Hello everyone, a very good evening and warm welcome to all of you. So let's wait for 5 to 10 minutes so that everyone can join the session. So yeah, hello everyone. Let's start the session. I hope I'm audible and visible. So a very good evening and warm welcome to all of you. My name is Pooja Verma. I'm PMRF Research Scholar from IIT Kharagpur. And instructor for this course is Professor Samal Das Mandar, Advanced Technology Development Center, IIT Kharagpur. This is a week 11 live interactive session of signal processing techniques and its applications. So you can use chat box for asking and interacting. So here first we will go through the some concepts and formulas which we will use while solving our assignment questions. Then move to the questions. Okay. So for this week, this is a multi-rate signal processing. So till now we have studied about the single rate signal processing, digital signal processing, signals or systems. So all the data which are sampled at the same rate and no change within the rate of the system is called single rate digital signal processing systems. If we are using more than one sampling rate to perform any operation, so it is called multi-rate signal processing. Here basically we are performing two operations. One is upsampling or interpolation. Another one is a downsampling or decimation. In the upsampling, we increase the sampling rate, or in the decimation part we reduce the sampling rate. So what are the decimation or down sampling? What is useful for? Why it is useful for? So it is useful for reduce the data for processing, create low computational count narrowband for narrowband filters, perform frequency translation, reduce power dissipation, that is P is equal to C V square F, where F is the frequency directly proportional to the sampling rate. This is the frequency. And it is likely to require less storage. While in the interpolation or upsampling, it is useful for effectively increasing resolution for digital to analog converters, useful for pulse shaping filters, and also useful for combining several independent narrowband channels into one wideband data stream. And it also simplifies the computations. So, what is a sample rate conversion? How we will convert the sampling rate. So let's xn is the sample and it is a box. This is convert the sampling rate having the system function hn comma m, and output of the system is y of m, where is the input sampling frequency and fy is the output sampling frequency. And this sample rate converter must be time varying, depends on input and output time. So ratio of the sample rates can be expressed as a ratio of two relatively prime numbers. Okay, where Fy is the output sampling frequency divided by Fx. Fx is the input sampling frequency must be equal to I by D, where I is the interpolator factor or upsample factor, and D is the decimation factor or downsample factor. Downsampling. This is a block diagram of the downsampling of any system. That input is the x of n, it is in sequence, and y of m is the output, and fx is the input sampling frequency and fy is the output sampling frequency. Then how downsampling is related to the input frequency and output frequency? It is related to the fy is equal to fx divided by d, where d is the downsampling factor, at which rate we down or the sample. So how we will do this the downsampling. Here is an example of the downsampling. Assume x of n is any signal that which is a causal. So x of n is the signal. There is a split that is 0 here, 1, 2, 3, 4 and 5. That is -1, -2, -3 and -4. So if we downsample by 2, then what will happen? Let's see what is the sequence of x of n. At 0, it is some value. Let's say it is 2. Then it is 1.5, and at 2 it is 1, or at it is 3 at n is equal to 3, and at n is equal to 4 it is 1, and n is equal to 5 it is 2. So how we will downsample this sequence? It is given that we have to downsample by a factor 2. So for downsampling, we just need to remove d minus 1 samples from this sequence. That is, d is given to 2 minus 1, that is 1 sample we have to remove from this sequence. Then we will get the downsample sequence. Okay, that is 2, 1, 1 and 2. Okay. And while we are downsampling the sequence, is there any difference in the time scale? Yes, there is a time contraction in the time scale by a factor n by d, where n is the time sequence and d is the decimation or a downsampling factor. Okay. Next, so the low pass filter SD of omega sufficiently reduce the spectral component of a omega is equal to pi by d. Thereby, the downsampler acts as an anti-aliasing filter. Okay, so downsampler acts as an anti-aliasing filter. In the ideal case, it is written by SD of omega of y is equal to 1, where mod of omega y must be less than equal to the pi or 0 otherwise. So for all the images except the primary image at k is equal to 0 term are removed, and y of omega becomes y of omega y is equal to 1 by d x of y omega of y by d, where omega of y must be less than equal to pi. So the decimation process can be viewed as a mapping of a signal in frequency from 0 to where omega x varied from 0 to pi by t to 0 and to omega y varied from 0 to pi. It mapped the input frequency to the output which carries the signal 0 to pi by t. It to map to omega y, that is output frequency, to 0 to pi. The low frequency components of the signal are expanded in the frequency in the time domain with corresponding in the contraction of the signal, or that is removal of the samples according to the decimation factor. So that one is up to downsampling or decimation, where we will decimate or reduce the number of samples from the sequence. And another one is a upsampling, that is interpolation. This is a block diagram of interpolation of, that is where x of n is in the sequence and v of n is the output sequence. Fx is the input signal frequency and Fy is the output frequency, where Fy, if any system which is upsampled by a factor I, then output is related to I is equal to f of x. This is the x of n sequence which is a causal, where 0, 0, 1, 2 and C. While we are doing the upsampling, what we are doing here, we are increasing the number of samples in any sequence. That means adding the I minus 1 0 in the sequence into the equally spaced between the sequence. Okay, so let's x of any sequence that is at 0 position. Let's it is 2, at 1 position it is 1, and at 2 position it is 3, and at the 3 position it is 2. So if upsampling by a factor I, let's I is equal to 2. So we will add I minus 1 zeros between the sequence, that is 1 0 between this sequence. So the upsampled frequency must be V of n is equal to 2 0 comma 1. After that I am writing here with 0 comma 3 comma 0 comma 2 or comma 0. Okay, this is a upsampled signal. The upsampling or interpolation is called anti-imaging filter, and it is represented by Hi of omega, where Hi of omega is related to a Hi of omega y is equal to I, where omega y, mod of omega y must be less than equal to pi by I or 0 otherwise. And Hi of omega y also can be written as these are the things. That is a compression in frequency of primary image with respect to the original spectrum of n corresponds to the expansion in the time scale of the signal. Here what we are doing, while we increasing the size of xn by adding 0, we expand the time scale. Okay. Now next one is the fractional rate conversion by I by D. What is a fractional rate conversion? The fractional rate conversion, what we are doing in here we are cascading the interpolation, interpolator and decimator. So both the system functions we are interpolating in one sequence. By it is a block diagram of fractional rate conversion system, where we are giving x of n to the interpolator, then we will find out the interpolated signal, that is Fp or Vp. It is Fp, where interpolated signal Fp is equal to I of Fx. Then we are giving the anti-imaging filter, then anti-aliasing filter, then we will giving to the decimator, that is a downsample the signal. So what is the relation between the input, output and interpolation and decimator factor, that is Fy by Fx must be equal to the I by D, or we can write it like I by D, first interpolating then decimating the input signal f of x. So the cascade interpolation and decimation filter, that is Hi of omega and Hd of omega, can be combined, form a single low pass filter, that is H of omega, or which is written by H of omega is equal to I, where mod of omega must be less than equal to minimum pi by I or pi by D. It must be equal to pi by I and pi by D. And that then combined signal system function is look like this. So the overall this system is converted to a single low pass filter, that is H of p, where x of n is given as the input signal frequency of f of x. Then it is interpolated by a factor I, then giving to the low pass filter. Then again we are decimating the sequence, and the overall representation is looking like this, where f of y is the output frequency, and output frequency is related to I by D f of x. If f of y is greater than f of x, then low pass filter acts as an anti-imaging filter. If f of y is less than f of x, then low pass filter will act as an anti-aliasing filter. And we have seen the sampling rate conversion till now in one stage, single stage. If we want to do sampling rate conversion in a multi-stage, then how we can do that? We have to divide this filter into a multiple fraction, or we can interpolate I and D into a multiple stages. So sometimes it will become a computationally more efficient to perform sample rate conversion in a multiple stages. So single stage decimator function or decimator system is represented by this block diagram, that x of n is the input sequence, f of x is the input sampling frequency, and it is given to the h of s, the function system function, and decimating by a factor d, then output we are getting fx by d. While if we use two stage decimator or multiple stage decimator, what we are doing? We are we are doing the decimator factor into multiple fraction, that is d must be equal to d1 into d2, or we can divide in the multiple mode stages, d1, d2, d3 or d4. It depends on the value of decimator. So here what we are doing, we are dividing the decimator factor into two stages. So what we are doing, fx is given as input signal frequency h1z to decimating by a factor d1. Then again we are giving to the other system function h2z. Then again we are decimating to the other factor, and that output signal can be represented as fy is equal to fx divided by d1 or d2, or d1 d2 is equal to d, so we can write it fx by d also. So the single stage decimated by a d1 into the first stage and d2 into the second stage, giving the overall decimator factor d is equal to t1 into d2. Now these are some of the topics which are required while we are solving the questions. So now we are moving to the questions or some set of problems. So the first question is, determine the expression of Vm as a function of input x of m for the multi-rate structure represented in the figure 1. This is a figure which is given is input signal x of m, and it is interpolated. This is a symbol of interpolation. So it is upsampled by a factor 5, then output signal is given to the anti-imaging filter. The upsampling frequency or upsampling system use anti-imaging filter. Okay, so what is a correct answer? Option A, Vm is equal to x m divided by 5, where m is equal to 0, 5 plus minus 10 or plus minus 15 for 5 sampling frequency, or 0 otherwise. Vm is equal to x 5 into m, where m is equal to 0, 5 plus minus 10, 0 otherwise. Option C is Vm is equal to x m divided by 10, where m is equal to 0, 5 plus minus 10, 0 otherwise, or option D is Vm is equal to x 5 of m only. So here it is giving the upsampling frequency. So we have seen that fy is equal to I into f of x, right? For our upsampling, so which we can obtain by adding I minus 1 0 in the input frequency. that is input sequence x of m. So here I is given 5, 5 minus 1, 0 is equal to 4 zeros must be added in the input sequence. So what will be the output sequence? So in order to find out the output sequence, it is a sampling frequency in terms of sampling frequency. If we want to expansion in the time scale, then what we have to do? We have to add 4 between the sequence 4 zeros. That means we are expanding the time scale by a factor x is equal to m by I. Here I is given by 5, that is m by 5 at a 0 in the interval of 5 5. Okay, so correct answer is option A. We are adding I minus 1 zeros between the sequence x of m, which leads to expansion in the time scale at a 5 5 distance. Okay, so option A is the correct answer for this question. Now next question. In a fractional rate conversion system, the input signal is sampled at 9 kHz and the output signal is sampled at 15 kHz. Determine the value of upsampling factor I and the downsampling factor D. Here, the input signal frequency is given as 9 kHz, right? And output signal frequency is sampled at 15 kHz, it is given. So as we know that what is the relation between the fractional rate conversion, Fy divided by Fx equal to I by D. We know that this relation. Now the output sampled frequency is given as 15 kHz and input sampling frequency is given as 9 kHz. That is I by D. So if we normalize this, what we will get? 5 by 3, right, is equal to I by D. So what is the interpolation factor and decimation factor? If we equate it, I is equal to 5 and D is equal to 3. So I is equal to 5 is the interpolation factor or upsampling factor and D is equal to 3. We got that is a downsampling or downsampler frequency. So which one is the correct answer? Option A is I is equal to 3 or D is equal to 5. No, we have got I is equal to 5 and D is equal to 3. So option B is the correct answer for this question. Okay. So I hope all of you getting the questions. Okay. So moving to the next question. What is the process of reducing the sampling rate by a factor 3? Option A is a sampling rate conversion. Option B is interpolation. Option C is decimation. Or option D is filtering. So any one of you want to answer this question? Please answer in the chat box. All of you have must be gone through the video lectures and also I have covered some theoretical part. So please answer in the chat box what is the process of reducing the sampling rate by a factor 3. Here we are reducing the sampling rate by a factor 3. So what that process is called? Sampling rate conversion. Option B is interpolation, option C is decimation or option D is filtering. So as we know that while reducing the number of samples from a sequence is called downsampler or decimation. It can be any factor, d is equal to 3 or 2 or 5 or anything. Just we are reducing the number of samples from the sequence. So it is called the decimation. So correct option is option C. Okay, so moving to the next question. In a fractional rate conversion system, if the input signal is sampled at 12 kHz and output signal is sampled at 8 kHz, then low pass filter acts as an option A anti-imaging filter, option B is anti-aliasing filter, option C is linear phase filter, or option D sub-band filter. So the question is given like in a fractional rate conversion system, if the input signal is sampled, let input signal that is f of x is sampled at 12 kHz and the output signal that is f of y is sampled at 8 kHz, then low pass filter acts as an. So let's see how the low pass filter will act. So as we know that the relation between fy by fx is equal to I by t. Okay, so output signal is given 8 kilohertz and input signal is given 12 kilohertz is equal to I by d. So what we will get 2 by 3 I by d, where I is equal to 2 and d is equal to 3, right? So in order to choose which one is the lower or minimum value, 2 or 3, the cutoff frequency of that filter must be pi by I or pi by d in order to choose the filter that is a minimum of the pi by I or pi by d. So what is a pi by I? That I is equal to 2 pi by 2 or pi by 3 minimum. So which one is a minimum? That is pi by 3. So what is this pi by 3? Pi by 3 is a d is nothing but the decimeter or downsampling frequency. So it downsamples the system by pi by 3, that is a downsampling frequency. Then this filter is downsampled, then it will act as a anti-aliasing filter, because while we are downsampling the frequency, then filter will be act as an anti-aliasing filter. If upsample or interpolate the signal, then that filter will act as an anti-imaging filter. So correct option is option B. Okay, option B, that is an anti-aliasing filter. Okay, so have you got? Are you getting these questions? Okay, so I'm moving to the next question. In a fractional rate conversion system, if the input signal is sampled at 16 kHz and output signal is sampled at the 24 kHz, then the cutoff frequency of a low pass filter will be. So this question is also related to sampling rate conversion system. So already we know that the relation of sampling rate conversion, the input signal, output signal, decimeter, interpolator, that is fy by fx divided by I by d. So fy, what is the value of fy? The output signal is sampled at 24 kilohertz and fx is given as 16 kilohertz, right? So fy is 24 divided by 16 is equal to I by d. So how much we will give? We got 3 by 2, right? That is equal to I by D, where I is equal to 3 and D is equal to 2. In order to find out the cutoff frequency of a low pass filter, we have seen that F cutoff frequency is equal to minimum of pi by I divided or comma pi by D. So minimum of I we have got pi by 3 or pi by 2. So in both, what is the minimum value? That is pi by 3. So the cutoff frequency of a low pass filter is pi by 3. Okay. So the correct answer is pi by 3. Okay. I hope all of you have got this question. So moving to the next question. Which one of the following are the advantages of a sample rate conversion by stages? Option A is reduced computation. Option B is quantization effects. Option C is fewer coefficients, reduce finite word length problem. Or option D is passband aliasing. So the question is, which one of the following are the advantages of the sample rate conversion by stages? So what are the advantages of a sample rate conversion by stages? So what we have is it reduces the competition process, or fewer coefficients reduces the finite word length problem. It also reduces the number of coefficients in any filter if we solve any question or any problem by sample rate conversion by different stages, or if we divide the decimation factor in the number of, so it will reduce the number of competition, or also fewer coefficients it will use. So correct option is option A and C are the correct option for this question. Okay. Okay. So moving to the next question. In interpolation by a factor 5, how many zeros are inserted in between two samples? So here interpolation factor is given I is equal to 5. So if any sequence having x of n, so how many number of zeros must be added between the two sequences? So already we have still I minus 1 zeros must be added in between the sequence in a interpolation. So I is given as 5, so 5 minus 1, that means 4 zeros added between the two samples. So correct option is option A, that is 4 zeros must be added between the two samples. Okay. Okay. So moving to the next question. I hope all of you got this question. So in a fractional rate conversion system, the input signal is sampled at 12 kHz. If the value of upsampling factor I is equal to 5 and downsampling factor D is equal to 3, then how many samples will be present in 30 millisecond output signal? So already we know that the relation between the output frequency and input frequency in a sampling rate conversion system is Fy is divided by Fx equal to I by D, right? So here input sample input signal is sampled, that means input sampling frequency is given as fx is equal to 12 kilohertz. And what are the other things are given? Interpolation factor is given, I is equal to 5, and decimation factor is given, d is equal to 3. So now first we need to find out the fy, that is output sampling frequency. So let's put all these values in this equation. Fy divided by fx is equal to I by t. So Fy is not given, Fx is given as 12 kilohertz is equal to I by d, that is I is equal to 5 and d is equal to 3. So what we will get, Fy is equal to here 3, 4, 24 into 5, 20 kilohertz. So we have got Fy is equal to 20 kilohertz. Now what is given, then how many samples will be present in 30 millisecond output signal. So in 30 millisecond output signal, how many samples are present? The output frequency is given and we need to find out the number of samples in 30 milliseconds. So in 30 millisecond output signal, number of samples are 30 milliseconds multiplied by 20 kilohertz. The output sampling frequency is given. So how many samples are present? That is 600 samples will be there in the output signal. Okay, so here option A is the correct answer. Okay, I hope all of you getting these questions and answers. If you have any doubt, you can ask. Otherwise, we can move to the next question. So all of you are noting these questions or solving with me. Any one of you can answer in the chat box or okay. So I will also suggest all of you, please keep one calculator with you so that you can calculate these answers by yourself also. Okay, great. So moving to the next question. Next question is question 9. What is the process of converting a signal from a given rate to a different rate? So what that process is called, converting a one signal from a given rate to the different rate. Option A is sampling, option B is normalizing, option C is sampling rate conversion, and option D is none of the mentioned. So till now we are solving the questions related to the sampling rate conversion system only. So if there is a signal which is given a specific rate and we are going to convert it into a different rate, so that is called sampling rate conversion. Okay, so option C is the correct answer. Or we can say that the process of converting a signal from a given rate to a different rate is called sampling rate conversion system. Okay, so option C is the correct answer. Okay, so moving to the next question. The sampling rate conversion can be as is shown in figure below, that this figure is related to the sampling rate conversion can be shown is this is true or false. So in the diagram we can see this is an interpolator. That means up here we are upsampling the signal. and it is a decimator, that is downsampling the signal. Okay, so what this is called, this is called sampling rate conversion system. We can say that. Here we can also see that the interpolator and decimator is cascaded together to perform action sampling rate conversion by a factor I by t, or we can say that Fy is equal to L by M into Fx. We have studied about I by d, but here interpolator is given by L and decimator factor is given by M. So L by M into f of x, that is a input signal. So it is a figure or this diagram related to a sampling rate conversion system. So true, this function is true. Okay. Okay, so can we move to the next question? Okay, moving to the next question. So question number 11 is number of stages S in a direct form FIR filter is given as H is equal to integer in brackets K into Fs divided by del F, where Fs is the sampling frequency, del F is the transition band, filter transition band, K is equal to 3, assume that K is equal to 3. If x of n is the signal with frequency range 0 to 2.4 megahertz, then the this is by the block diagram, then the signal is sampled, I think, at 400 megahertz. Here it is given, and the block diagram of the function, the two-stage filter, or this is a two-stage decimator system, where low pass filter is input signal is given to the low pass filter 1, then it is decimated by a factor 50, then it is given that output to low pass filter 2, then again that output is decimated by a factor 2, then we are getting the overall output Y filter, and the assumptions are like given as passband frequency of low pass filter 1 is given 1.8 megahertz, stop band frequency of low pass filter 1 is given 4 megahertz, pass band frequency of low pass filter 2 is given 1.8 megahertz, and stop band frequency for low pass filter 2 is given as 2 megahertz. Both filters are having flat pass bands and stop bands. It is also given. Pass band attenuation for both filter is 0 dB and stop band attenuation of both filters is infinite. It is given. So calculate total number of stages, that is as low pass filter 1 plus as low pass filter 2. So total number of stages in low pass filter 1 and low pass filter 2. So now how we will get this question? How we will solve this question? So it is given the number of stages, we can find out the this formula. So I hope I have not taken any extra. Okay. So I am solving here, then I will remove that. So please, I will suggest you please note down with me. So number of stages, that is S, is given as, in the question it is given as integer of, here I am writing only int, okay, K into Fs divided by del F, where del F is the transition bandwidth, or Fs is the sampling frequency, K is a constant which is here it is given, we need to assume it 3. So now Fs is given and we need to find out the del F, that is filter transition band, and the input frequency range is given 0 to 2.4 megahertz, and here it is, but its sampling frequency fs is given 400 megahertz. I will correct it while uploading the slide. So here the sampling frequency is given as 400 megahertz. Okay, that is 400 megahertz. And also we know that fs is equal to 1 by ts, right? So the input signal is sampled. We know that x of n is sampled x of nts, and this nts I'm writing after that x n by fs. We can write it like this also. So first we need to find out the input sequence. So x in brackets n divided by 400 megahertz. Okay, so this is a signal which is going to a low pass filter 1. So now for low pass filter we need to find out the parameters or number of filters which we will calculate from this number of stages, how many stages for low pass filter 1. So input x of n after sampling. So for low pass filter 1, number of stages, low pass filter 1, number of stages is represented as S1. Let's, so it is given as k into fs divided by del f, or this is a integer, must be integer function, right? So here k is given 3, k is equal to 3, fs is equal to 400 megahertz, and transition band or del f, how we can calculate the transition band? I am writing it is del f. So that is a low stop band frequency, stop band frequency minus pass band frequency. So what is a stop band frequency and pass band frequency for low pass filter 1? It is given pass band frequency of low pass filter is 1.8 megahertz and stop band frequency for low pass filter 1 is 4 megahertz. So stop band frequency is given as 4 megahertz minus 1.8 megahertz. It is in megahertz. So you can write it out. So how much we will get? That is 2.2 megahertz, right? So transition band for low pass filter is 2.2 megahertz. Okay. So I hope all of you noted down till here. So I am removing till here in order to write it down. So yeah. Okay, you can ask Jessica.
हेलो मैम.
Yeah,
हाँ,
yeah.
यस मैम, ये 400 मेगाहर्ट्ज कैसे लिया?
400 megahertz, actually it is given here. See in the slide, actually my block diagram has
ओके
overrides
ओके
over.
ओके
So it
ओके
is given
देन
here.
ओके
I will
ओके
correct
ओके
it.
यस यस ओके थैंक यू मैम.
Okay. Okay. So I am removing from till here. Please, I hope all of you noted down. After that, I will write. Okay, so transition bandwidth we have got 2.2 megahertz. So now, as we know that S1, here we need to put all these values. So integer of k is given as 3. We it is given, let's assume k is equal to 3, and fh is the sampling frequency. It is given as 400 megahertz. It is given, please, here it is overwritten by this block diagram. I will correct it and then upload it. Okay, it is given 400 megahertz is given, 10 to the power 6. Then del f, that is transition value, 2.2 megahertz. 2.2 megahertz. Now what we will get, if you 10 to the power 6, 10 to the power 6 will be cancelled out, and if you multiply 3 into 400 and then divided by 2.2, you will get 545.45. Okay, now we have to take the integer value only, it is given. So how much we will get? 545. Okay, so number of stages for low pass filter 1 is 545 we got. Okay, note it down. Now it is S low pass filter 1 we have got, that is S1. Now we have to calculate this part, S2. I am writing it is given as S low pass filter 1, and we have calculated. Now we have to calculate low pass filter 2. Okay, so now after getting here, I am removing from here. I hope all of you noted down. So can I remove it? In the same way, we have to calculate the number of stages for low pass filter 2. Okay, so I am removing it from here. Okay, so for low pass filter 2, I am representing the number of stages by S2. Okay, so here after getting the all those the signal, here we are decimating by a factor 50. So input signal x of n is decimating by a factor 50. So what we are doing, decimation is nothing but the reducing the number of samples or compression. Okay, so decimation by a factor n by fs, that is x by n. Here the sampling frequency, here we are getting fx, or in terms of fx and fy, we have divided n by fs or n into ts. Already we have shown that n is equal to 4 into 10 to the power 6, and this signal is decimating by a factor 50. That means n into 50 divided by 410 to the power 6, right? So what we will get, the input sampled frequency for low pass filter, that is decimated by 50, that is 400 megahertz must be decimated by a factor 50. So here we will get, if you divide and multiply this 0, 8 into 10 to the power 6, right? So for low pass filter 2, the sampling frequency is 8 megahertz, right? We have got the sampling frequency for a low pass filter, it is 8 megahertz. fs2 I am writing here. Okay, 8 megahertz. Now what we need to find out, the transition band, that is del f2 for stage 2 I am writing. So del f2 is Fs, sorry, or we can write omega s, or you can stop band frequency minus pass band frequency mod of. So for low pass filter to stop band frequency, here it is given 2 megahertz, and pass band frequency for low pass filter 2 is given 1.8 megahertz, right? Megahertz. So what is the value? That is 0.2 megahertz. The transition band for low pass filter 2 is 0.2 megahertz. Now we have to calculate the number of stages for a filter, low pass filter 2. So I hope all of you noted down till here. I am going to remove it from here so that I can write. So just remember that we have got S1 545, or we can write it as low pass filter is 545. So now we have to again put in this equation, that is S2 is equal to integer k into Fs 2 for low pass filter 2 into del f 2. Now I am writing here. So again it is given k is equal to 3. Now what is the sampling frequency for the stage 2? What we have got? 8 megahertz, right? And del f2 we have got 0.2 megahertz. So this one will be cancelled out. How much we will get? If you do that, so you will get 120. I think 3 into 8, or if you multiply and divide this, you will get 120. Okay. So number of stages in the low pass filter 2 is 120. So now we have to calculate total number of stages, that is low pass filter 1 plus low pass filter 2. So total number of stages is equal to S1 plus S2. Here I am writing in place of S a low pass filter 1 plus low pass filter S1 plus S2. Okay. Removing from here. So S1 we have got 545, right? And S2 we have calculated 120. So total number of stages is 665. Correct? So total number of stages is 665. Okay. So I hope all of you understand this question. If you have any doubt, you can ask. So this type of problem we have to solve like this. If we divide the multiple uh, any system in the multiple stages, so their pass band frequency, stop band frequency must be given, or you can take as an assumption. So total number of stages you can calculate. This type of questions you can expect in the exams. Okay, so I hope all of you got this question or understand. So we can we move to the next question? Can we move? Anyone can answer it? Okay. Okay, so moving to the next question. Okay, so the next question is which of the following operation has to be performed to increase the sampling rate by an integer factor I? Option A, interpolating I plus 1 new samples, or option B, interpolating I minus 1 new samples, option C, extrapolating I plus 1 new samples, or option D, extrapolating I minus 1 new samples. So anyone want to answer this question? Please answer in the chat box. Which of the following operations has to be performed to increase the sampling rate by an integer factor I? Here in the question it is we need to increase the sampling rate. So how many zeros must be added in the sequence? In order to increase the sample, we need to interpolate between the sequences, right? So we have seen that I minus 1 new samples or zeros must be added in the or between the samples. Okay, so option B is the correct answer for this question. Interpolating I minus 1 new samples between the sequences. Or the explanation is given as an increase in the sampling rate by an integer factor of I can be accomplished by interpolating I minus 1 new samples between successive values of the signals. Okay? Okay. So moving to the next question. Okay. So next question is, what is the folding frequency for the Eliased version of x of n with sampling rate f? Option A is given f by d, option B is given f by 4d, option C is given f by 2, or option D is f by 2d. So here what is given? What is the folding frequency for the Eliased version of x of n with the sampling rate f? Sampling rate is given here as f. So here the decimation factor is only given. Okay, right? In the while you are seeing the options, or in that type of question you have to just focus on the options, what is given, interpolation factor given or decimation factor. So in the all the options, the mostly decimation factor is given, right? So folding frequency for the Eliased version of x of n of the sampling rate is must be f by 2d. So the explanation is given as, we know that if we reduce the sampling rate by selecting every dth value of xn or decimating the value at d or d factor, the signal will be Eliased version of xn with the sampling folding frequency f by 2d. Okay, so option D is the correct answer for this question. Okay. Okay, so I hope all of you got this question, so we can move to the next question. Okay, so the next question is, which process has a block diagram as shown in the figure below? This block diagram is related to the which process? So let's see what is this block diagram. So block diagram is given as the input signal x of n is given to a low pass filter, that is h of z, which having cutoff frequency is plus minus pi by m. 1 in the range between minus pi by m to pi by m, and then this signal is given to a downsampler that is factor m, and then we will find out the output signal. So this block diagram related to which process? Option A is sampling rate conversion, option B is interpolation, option C is decimation, or option D is none of the mentioned. So from the block diagram, we can clearly see that this is a downsampler. Okay, so here we are downsampling or decimating the sequence by a factor m. So this block diagram is related to a decimation only. So option C is the correct answer for this question. Okay. Okay, so moving to the next question. I hope all of you understand this question. Okay, here also again take a D. If Hd of omega is the frequency response of a low pass filter, then for what value of omega, that is Hd of omega is equal to 1, for which what value the filter will be the 1. Here Hd of omega is the frequency response of a low pass filter. It is a frequency response of a low pass filter. So for what value the filter will be 1. Option A is mod of omega is equal to pi by d. Option B is mod of omega must be greater than equal to pi by d. Option C is mod of omega is less than equal to pi by d, or none of the mentioned. So for what value of omega, that filter function must be 1. So for what value it will pass the signal. So while you have gone through the video lectures, or we have also discussed about these things in the previous slides, so the value that must be passed the signal must be equal to pi by d. Here the decimation factor is only given, so pi by t. Otherwise, if there for any sampling rate conversion system, the value function must be pi by I or pi by d, whatever you will choose. If the interpolation is only given, so Sd of omega must be 1 for the values of Sd of omega must be less than pi by I only. Okay. So the input sequence x of n is passed through a low pass filter characterized by an impulse response h of n, and the frequency response Sd of omega is given, which ideally satisfies the condition Sd of omega is equal to 1 for values of omega. Mod of omega must be less than equal to the pi by d or 0 otherwise. Okay, so option C is the correct answer for this question. Mod of omega must be less than equal to pi by d. If decimation and interpolation both the factors are given, then minimum of pi by I or pi by t. Okay. Okay, so I hope all of you got this question. So moving to the next question. Sampling rate conversion by a rational factor I by d is accomplished by a what connection of interpolator or and decimator? Option A is parallel, option B is cascade, option C is convolution, option D is none of the mentioned. So already we have seen that in the slides and in the lecture video you have seen sampling rate conversion system by a rational factor. What is the relation? Fi by Fx is equal to I by D, or output of a system is I by D into f of x. It is connected by first interpolation, then low pass filter, that is h of n, then decimator, then output y of n, and it is given as x of n. The input sampled frequency f of x and output sampled frequency is f of y. It fy of y is related to I by d into f of x. So it is a cascade connection. Any sampling rate conversion by a rational factor I by d is accomplished by cascading and interpolator and decimator. So it must be a cascade connection only. Sampling rate conversion by a rational factor I by d is accompanied by a cascade connection of interpolator and decimator. Okay. Okay, I hope all of you got that question. So moving to the next question. Okay, So next question is, for designing a multi-rate low-pass filter with pass band 0 to 50 Hz, stop band 60 to 280 Hz, stop band deviation is 0.001, pass band deviation is given 0.01, and sampling frequency f of s is equal to 400 Hz. What would be the value of normalized transition bandwidth? Transition width. So how can we move to the with this question? So what is the transition width? First we will know that. So the region which is in between the pass band and stop band is known as a transition region. We know that, and also we know that the transition bandwidth or transition bandwidth width is represented by the stop band frequency minus a pass band frequency. Okay, so this is a normal transition width. If we normalize the transition bandwidth, so what we need to do, we have to divide it by a sampling frequency, or otherwise you can represent in the form of fs minus ft. Okay, so here we need to find out normalized transition width, that is this one, del omega by fa. So let's see what are the values are given. So here for designing a multi-rate low pass filter, pass band 0 to 50 Hz is given. The pass band frequency is given, that is omega p 0 to 50 Hz. So last frequency is 50 Hz. So pass band frequency is 50 Hz only. And stop band is given 60 to 280 Hz. The stop band range. So it is started from a 60 Hz. So stop band frequency is 60 Hz only. Okay. So what will be the del omega? Then stop band frequency, that is 60 Hz, minus this pass band frequency, that is 50 Hz. It is in all Hz. So 10 Hz. So now what is normalized transition width we have to find out. So how we will get the normalized transition width? Divided by sampling frequency. Normalized transition width is del omega divided by sampling frequency. So del omega we have got 10 Hz. Sampling frequency is given as 400 Hz. 0 and 0 will be cancelled. What we will get? 0.025 Hz. Okay. If you calculate this 1 by 40, you will get 0.025 Hz. So correct answer is 0.025, option A. Okay. So normalized transition width is 0.025 Hz. Okay. Option A is the correct answer for this question. I hope all of you got this question. So can we move to the next question? Can we move? Please answer. I'm audible. Okay, great. Yeah. Please answer in the chat box so that I can also understand that all of you getting this question. Okay, so moving to the next question. So next question is given as, consider the assertions steps given below. Which among the following is the correct sequence of designing steps for sampling rate converter? So these are the some steps which are given. We have to arrange these steps in the ascending order for designing a sampling rate converter system. So A is computation of decimation or interpolation factor for each stage, clarification of anti-aliasing, anti-imaging filter requirements. C is designing of filter at each stage, T is calculation of optimum stages of decimation, interpolation, yielding maximum efficient implementation. So which one is the correct sequence from these options? Option A is A, B, C, D. Option B is C, A, D, B. Option C is D, A, B, C. Or option D is B, D, A, C. So what are the steps while the designing a sampling rate conversion system? What are the basic steps? So see the assertions or steps. So what we need to do first, we need to find out whether it is anti-aliasing or anti-imaging filters. What are the requirements for the decimation or interpolation or clarification of anti-aliasing or anti-imaging filter requirement? B. Then Dejanu we have to join last computation. Okay. Then next is calculation of optimal stages, decimation, interpolation, yielding maximum efficient interpolation, implementation. Then B after D. Then computation of decimation or interpolation factor for each stages. Then C, designing a filter at each stages. Okay, so correct option is B, D, A, C. Okay, so correct option is D. Okay, so I hope all of you got this question. Okay, so moving to the next question. So correct option is D. The sequence must be B, D, then A, then C. Okay. Okay, so moving to the next question. What is the relationship between omega x and omega I? Here option A is omega y, it is omega y is equal to omega x into I. It is also omega y is equal to omega x divided by I. Option C is omega y is equal to omega x plus I, or option D is none of the mentioned. So what is relation between omega x and omega I in terms of interpolation? Here the interpolation factor is given I. So first through the option, then think about this, then answer. So what is the relation between omega y and omega x in terms of interpolation or upsampling filter? So already we know that the relation between for interpolation is fy is equal to I into f of x. Okay, or it is given in terms of frequency. If we written in terms of omega y and omega x, then it must be omega y is equal to omega x divided by r. So option D is the correct answer. Okay, the relation between omega x and omega I is equal to omega y is equal to omega x divided by I. Okay, option B is the correct answer for this question. Okay, I hope all of you got this question. So moving to the next question. Consider a sequence x of n is given as 246801357 downsample the sequence by 3 and then upsample by 2. The resulting sequence is. So let's see how we can do that. Sequence x of n is given 2, 4, 6, 8, 0, 1, 3, 5, 7, 9. Right? So what we need to do first, downsample the sequence by 3. First we need to downsample by 3. So down sample by 3, that means x of 3n. So what we need to do? We have to remove between the two sequences, so t minus 1 terms. That means 3 downsample by 2, 3 minus 1. That is downsample by 2 factor. So what we need to do? We just remove this two samples in these sequences in every. So 2, what we will get? 2, 8, 3, 9. Right? We will get 2, 8, 3, 9. After downsampling, now what we need to do? Upsample by 2. So upsample by 2 in the resulting sequence. So 3n divided by 2. So what we will need to do? Upsample by 2. So between the two sequences we need to add I minus 1 0. So I is given to 2 minus 1, that is 1 0. Between these sequences we need to add 1 0. So how we can write it? So 2, then we have to add 1 0, then 8, again we have to add 1 0, then 3, again we need to add 1 0, then 9, and after 9 we have again add 1 0. So this is a upsampled by 2 sequence. So the resulting sequence after downsampling then upsampling we will get 2 0 8 0 3 0 9 0. So which one is the correct answer? Option C is the correct answer. 2 0 8 0 3 0 and 9 0. Okay. Okay, I hope all of you have got this question. So can we move to the next question? Okay, so moving to the next question. So next question is, decimation is the process of, option A, it's retaining sequence value of xpn other than zeros, retaining all sequences values of xpn, dividing the sequence value by 10 or multiplying sequence value by 10. So they have asked only for decimation is the process of. What is the process of decimation? So what we are doing in the decimation, that any sequence xp of n is given. So by a decimating, what we are doing, let's xp any value, our decimating factor, let's a into n. What we are doing? Removing the number of zeros or removing that number of sequence. So what we are doing, retaining the sequence values of xpn, we are retaining the same values other than the zeros. So let's the sequence that xp of n is given as -5 2 3 2 -2 7. Let any sequences like this is given, and we need to decimate by a factor 2. The decimation factor, that is d, is given as 2. So what we need to do, we have to remove between these sequences t minus 1 terms, right? So d is given 2 minus 1, that is 1 terms we have to remove between these sequences in order to decimate. So the new sequence we will get 5, then 2, then 7. Yeah, someone is asking question. Just a minute, I will reply. So what we are doing, we are retaining the sequence of values of xpn other than the zeros. Okay, yeah. So option A is the correct answer for this question. Could you once check the answer of question 19? Okay, 2 pi f. So question number 19. Okay, let me check. W is equal to 2 pi f, correct, and fy is equal to I into xi f. Question number 19. Please check 2 pi f, correct. Yeah, I will see this question again. Bhagya Prasad. Yeah. Hopefully a wx into I, but it is for decimation or interpolation. I will check it. Okay. Okay, so I hope all of you got this question. Decimation is a process of retaining the sequence values of xpn other than the zeros. Okay. Okay. So moving to the next question. So the next question is, a digital audio system exploits oversampling techniques to relax requirements of the anti-imaging filter. So the overall filter specification for a system is given as baseband signal is given 0 to 20 kHz, input sampling frequency is 44.1 kHz, output sampling frequency is 176.4 kHz, stop band attenuation is given 40 dB, pass band ripple is 1 dB, transition bandwidth is 2 kHz, stop band edge frequency is given as 22.05 kHz. So what we need to do, design a suitable interpolator. So how will we will design the suitable interpolator? So how we can design the interpolator? So as we know that we can design a single stage or multi-stage. So we will check on both stages. The interpolation it is given like I into f of x, right? So interpolation factor is f of y divided by f of x. So the input sampling frequency, that is f of x, is given 44.1 kilohertz. F of x is given, and f of y, output sampling frequency, is given 176.4 kilohertz. Right? It is given. So the interpolation factor, what we will get, 176.4 kilohertz divided by 44.1 kilohertz. So kilohertz will be cancelled. If you divide, you will get a 4. Right? So interpolation factor, we will get I is equal to 4. So the system can be implemented by a single stage with factor 4 or two stage interpolation factor of 2 in each stages. So I is given 4. Okay. So if we want to design a single stage with factors, so first single stage with I is equal to 4. Just start having it here from here so that first one is single stage with I is equal to 4. So how we can design the interpolator? Here it is the input sequence x of n, and the input frequency is given as 44.1 kilohertz. Now it is a y of n. The output frequency is 176.4 kilohertz. It is given. So we have got the interpolation by a 4 when it will pass anti-imaging filter H of n. This is a single stage interpolator system. Okay. Now, if we want to design a two-stage, then what we need to do? So I please note it down so that I can remove. Then I will go for two-stage interpolation. So can I remove this? Removing from here. I hope all of you wrote it down. Yeah. So are you getting these questions? Okay, great. Okay, so till now we have designed for single stage, that is interpolation factor is 4. Now we will move to the two stage. Okay, so second one is two stage with interpolator. So what we need to do here, I is equal to 4. So for two stage we have to divide it into two terms. So that can be 2 into 2. That means I1 is equal to 2 and I2 is equal to 2. Right? So what will be the? This is I1 or stage 1. Then it will move to the stage 2, that is I2. In the stage 2, in the interpolator or any filter, what are the sequences? One is interpolator or decimator, or other one is a anti-imaging or anti-aliasing filter, right? This is output, overall output. This is input. That is input frequency is 44.1 kilohertz, and output frequency is 176.4 kilohertz. Now in the I1 also there is one interpolator and anti-imaging filter. So interpolator by a factor 2, one is here, and second one is interpolator factor by a 2. So one anti-aliasing for H1n and this is a H2n. So what will be the frequency here? It is a Vm. So what will be the Vm? What is the frequency of Vm? Input frequency is given 44.1. The interpolation factor is 2. So frequency will be the 88.2. Here 88.2 kilohertz. The frequency. If you again multiply it by 2, so you will get 176.4 kilohertz. So it is a two-stage interpolator system. Okay. So if the question is given like this and you are asked to design an interpolator, so you have to go through these machines. First single stage interpolator, then second stage. And if you can further divide it, you can design with that only. Here I is equal to 4 only, so I have taken two stage interpolator function. Okay. So I hope all of you have got these questions. Any one of you have any doubt, you can ask. Otherwise, today I have completed this question set. Today I have taken 22 questions. So if you have any doubt, you can ask. Otherwise, we can close the session. Thank you. Oh yeah, Bhagya Prasad, I have to rectify this. Okay, yeah. What is the relationship between Wx and W omega x and omega y? Yeah, 2 pi by, but if we change it, y into 2 pi fx into I, but in that it is given as omega x divided by I, or it is opposite to omega y. Let me check once in the slides. Will back to you. Yeah, which question? I think I or D should be mentioned in the question. Which question? Question number 19. Yeah, if this type of question, if I or D is given, so you have to assume that whether it is an interpolator or a decimator. There is one more question where D is given. So by seeing options, you have to answer this type of questions. Okay, let me check once, then back to you. Oh, I hope all of you have gone. It is normalized omega x and omega y are the sampled input sampling frequency, but if you normalize this 2 pi f divided by fy, it must be. If you change like this, then it will get omega x divided by I. Okay, if you take like this, I hope so, 2 pi into f divided by fy, or it is fy is given I of fx, right? So in order to find out that in term of omega y is equal to omega x divided by I, so it is given in normalized form 2 pi into f divided by fy, and here also 2 pi f divided by fx into I. Now these terms if they cancel out, so fy is equal to fx into I. Okay, Bhagya Prasad. Hello. Yeah, it is in the terms of normalized frequency. So you have to go like this in this. Okay, so now you got this. So you will get from there omega x divided by I. Okay. Okay, so I hope all of you understand. If you have any question, you can ask. Otherwise, we can close this session. Okay, so thank you everyone. Thank you for joining. So now we are closing this session. Okay.